All right, guys. Talk today about graphing. Obviously, a few more polar points. Then start talking about how we convert back and forth between the two. How you take a rectangular point and make it into a polar point, or vice versa. And that's not too hard. That actually goes back to what you know from chapter 5, which is also, if you think about it, chapter 5 was what we learned in geometry class as a 9th or 10th grader. So we've got some stuff here that's not a lot difficult to do, but I want you to understand that it is the foundation for what we're going to do in the next 3 to 3.5 weeks. So if we don't pick up on this quickly, we might struggle with some of the concepts that this is going to lead into. And some of these concepts you guys already know from physics. You guys have dealt with vectors in physics, right? Okay. A vector is a directed line segment. Have you heard that phrase before? Or a line segment that has a direction and a distance. Okay. And there's a lot of quantities that we like to represent that way. Forces being one of them. You might start to recognize and see a lot of the formulas that you dealt with vectors in physics class that you were probably just given. They're going to start showing up today, and you're going to maybe see, maybe in physics they were hard because you weren't seeing where they came from. Today you're going to see they come from something very simple. Okay, so it might be or might allow you to use them a little bit easier if you recognize where they come from. So here it says let's plot the following points. I just want to plot 7 comma pi over 2. So yesterday we talked about, the day before, we talked about taking 7 pi over 2. First thing you're going to do is trace out the angle. Find where pi over 2's terminal ray exists. Okay. That is the best thing to do. There's a couple times I said it doesn't really matter, and it doesn't. The only time it matters, whether you go out to the circle first or you do the angle first, is when the radius is negative. And then you have to do the angle first. It's just the safest thing to do. So if that's the issue, then we might as well always do the angle first. Does that make sense? So I do the angle first, go out, find pi over 2's terminating ray. And now all I'm going to do is count. I'm going to turn that off. I just count 7 circles on that ray. Okay? So count 1, 2, 3, 4, 5, 6, 7, and it should put my point right there. So I'm looking at, when we do polar coordinates, we're looking at the intersection of a terminal ray that is defined by some angle measurement and a circle of some radius. In this case, the radius is 7. So the intersection of those two things is that yellow point. Is that all right? Okay. Let's do another one. Okay. If I do -7 comma negative pi over 2, this is where it matters that you do the angle first. So we go negative pi over 2. We know negative pi over 2 is going to provide that angle right there. Okay, because negative means we go in the clockwise direction, correct? Okay. And if it was just 7 comma negative pi over 2, we would count out 7 circles. But -7 means you count out 7 circles on the opposite side of the pole. Okay, so we write this out, and then the opposite side of the pole would be up here. Does that make sense? Okay, so I count out 7 circles, and where is that going to get me? Yeah, it gets me in the same exact spot. And that's what we talked about maybe briefly yesterday or the day before, is that we now have 2 different ways to write the same spot or to reference the same spot. Okay. If I go 7 comma 5 pi over 2, 5 pi over 2 is bigger than 2 pi, isn't it? Okay, that's 4 pi over 2 plus pi over 2. So 4 pi over 2 would be 1 complete revolution. And then add pi over to that, it would get me right there to that terminal ray again, right? If I count out 7 units on that terminal ray, is that going to be the point that I get? So there's a third way of identifying that point. If I go 7 negative 3 pi over 2, trace out negative 3 pi over 2, so it's going that direction. It's going clockwise again. Okay. So I get that terminal array, and I'm going to go 7 out on that terminal array, and it gives me that point there. All right, so what are we seeing? We're seeing that unlike the rectangular system, in the polar system, we have multiple ways of identifying the same point. Okay, and that can be problematic sometimes if we don't pay attention to directions that are explicit, or maybe even directions that are implicit. Okay, usually, you know, if I'm thinking about maybe using these polar points to do something else with, to do further calculations, if I have, for instance, the fraction 50 over 100, do I want to take that 50 over 100 and run it through another operation, no matter what that other operation is? Or would you rather take 1/2 and run that through other operations? 1/2, right? You would like to deal with the smaller values, okay? So if I have an angle of 5 pi over 2, wouldn't it be easier when I'm running through other operations? Wouldn't it be easier to deal with pi over 2 instead? Okay? So usually the idea of the process, the logic is when you are messing around with these things, and in whatever format they provide you, if you have angles that are larger than 2 pi or larger than 360, you usually want to use your coterminal principles and depreciate them. Make them between 0 and 316, between 0 and 2 pi, because it's going to make your math a little bit easier to deal with. Okay? I'm a person that I don't like negative angles either. Okay? So if I have negative pi over 2, I'm going to change that. Okay? I'm going to change it to 3 pi over 2. Okay? Is that all right? And eventually, as we start getting the hang of this and recognizing these relationships, if I ever start with like -7, comma negative pi over 2, I'll probably never deal with that -7. Okay? Or depending on the next thing I need to do at that point, might dictate whether I use -7 or not. Okay, so those are just some things to think about. I think I said this yesterday, it's the nice thing about polar coordinates, but at the same time, it can be problematic because you might be working with a friend and you came up with one solution, they came up with another solution, so you think, well, one of us is right, one of us is wrong, when indeed both of you might be right. Okay? Or Zach, both of you might be wrong. All right, so let's take a point in the rectangular coordinate system and convert it to polar coordinates. Okay? Would you guys agree? So 3, 4, let's say that you are standing on 0, 0, and you want to get to 3, 4. Okay? In rectangular systems, we cannot travel. Let's see here. Where's my tablet? I'll do all that. All right. Let's say that, you know, these regions in here that I'm coloring in, okay, we cannot travel through them. Okay? A lot of times the idea that I'm trying to kind of deal with here, talk about, is called taxi-cab geometry. And the fact that I don't want to travel through these. Okay? Think about like New York City is a bunch of parallel perpendicular lines in regards to their streets, right? Okay. Can I, if I'm a taxi cab right here, can I get to there by driving that direction? No. I got to go all along the streets, right? I can't go through buildings. So a lot of times this idea of only moving on the grid lines is referred to as taxi cab geometry. If I am interested in going from that position right there, 0, 0, to 3, 4, using that concept, no matter how many different routes I go, okay, if I count the amount of horizontal and vertical distances that I travel, that should always equate to 7, shouldn't it? Okay, so I'm going over 3 horizontally, and then I'm going up 4 vertically. So traveling 7 units might be problematic, right? What would always be shorter? Yeah, straight there, right? Now, obviously, if we're thinking about taxi-cab geometry, we would not do that, but there are reasons why it might be a little bit more efficient to go straight from 0, 0 to 3/4. Think about maybe you're interested in robotics. Okay, if I've got a robot that has to take something from point A to point B, and I program it to move from here to there to there, okay, using those directions, that's not very efficient, right? Maybe that's a lot of unnecessary wear and tear on the components of that robot, right? Wouldn't it be easier to program it to go from here straight along that line, okay? And every time that we do that, every time we go along a segment that is not vertical or not horizontal, that segment is the hypotenuse of some invisible right triangle, isn't it? Okay. And in this case, that invisible right triangle, we should know because of what we understand with the coordinate plane. It is that right triangle with legs of 3 and 4, right? Okay. So my question to you is, how do we go from that 3, 4 to providing now a way to go from 0, 0 to 3, 4, but using that radius, traveling along that blue line? We need to know how far do I travel on that blue line? And the second thing I need to know is, well, what angle is that blue line positioned with the positive x-axis so that I know that I'm traveling towards 3, 4? Does that make sense? If I have the wrong angle, then I might kind of divert away from 3, 4 unintentionally. So, how do we go about doing this? How can I find, let's just do R first. How can I find R from that information up there? Pythagorean theorem. 7th and 8th grade math, right? Okay. So we can do the Pythagorean theorem. We say 3 squared plus 4 squared equals R squared. So then R is 5. So I know that I need to travel on that blue line a distance of 5 circles, okay, or 5 units in this case. Now think about that. How does that compare to the distances in rectangular form? The distances in rectangular form sum was 7, right? The wear and tear on my robot is now depreciated because now I only have to travel a distance of 5 units. Okay. Tangent of theta equals 4/3, doesn't it? Okay. Now I'm going to use tangent, and usually textbooks do. People are saying, well, why didn't you use sine and cosine here to find theta? Because I want to be able to find R, and I want to find theta from just the information that's provided in the point, the ordered pair x comma y. Does that make sense? So I don't want to have to, I want to just use 3 and 4 to find R and 3 and 4 to find theta. I don't want to have to use a new number to help me find theta. So now if I want to find theta, then I just use the tangent inverse key, okay, or function, the arctangent, and then the polar coordinates become those values there. Now that is in radians, okay, so it might be beneficial as you guys are writing these things. Let's see here, let me end the slideshow real quick. All right, it might be beneficial to write your solutions kind of like this, 5. If I write 5 comma 0.93, it still looks rectangular, right? Looks like an x value and a y value. So it probably makes sense to, at least by hand, writing on a test or a quiz or something like that, put radians in there. I think on WebAssign, obviously the question is going to be assigned that says, here are rectangular coordinates, put your answer in polar form, so then it's known that those are radians or maybe degrees, but just be cautious of that, okay, especially when you're working on paper and you're going back and forth a lot, and some of the calculations that we do later on, we might have, we might transfer back and forth 2 or 3 times between polar and rectangular. And if you're not making sure that you're organized with your work and labeling things, you might forget what format a certain set of points are in. Does that make sense? So using that labeling is very important. Okay. Now there's a couple other ways that you might want to write these. Say I was interested in degrees. Okay. Just kind of give myself a little bit of room here. If I was interested in degrees, if we did this thing, I think it's 50 something degrees, 53 degrees or something like that. Let's double check here. Arc tangent of 4/3 in degrees, 53.13. So you could write this as 5, comma, 53.13 degrees. Again, paying attention to directions, it might say write it in terms of theta being radians or theta being degrees. It might tell you to specify a certain decimal place. If it doesn't say specify a certain decimal place, this is what they're going to want. Does that make sense? Okay. Is that the exact value for that 0.93 or the exact value for the 53.13 degrees? Okay. And now here is something that you might think about as well. If I guess we'll do an example here in a little bit of this. Yeah, so those are your couple different options for writing your answers. I did see, as I was creating the homework assignment, there were a couple answers that looked this way. So just be cautious of that. Okay, pay attention to directions. I think you guys will be okay with that. Is that all right? So we see that when we convert from rectangular to polar, it's simply just SOHCAHTOA and a Pythagorean theorem. Okay. So what we do then is say, if this is the case, let's just make it arbitrary. Let's use some just generic values for x and y. So here is your generic x and y ordered pair. Okay, if I'm going to mess with that generic ordered pair, we have the argument that x squared plus y squared should equal r squared, right? And then we have r is equal to x squared plus y squared underneath the root. Okay. Going to physics, you guys talk about the magnitude of a vector. Okay. Is that the formula you use for the magnitude of a vector? It's just the length of a vector, right? And it's just the length of a radius of some sort, okay? Or the length of the hypotenuse of some right triangle. Okay. Now they might have used the times that I've messed around with physics courses. A lot of times the x and the y, for some reason they use a and b. I don't know. It depends on what I guess textbook you're using or whatever. But that might be something you've seen. Okay. And they might not have even used, in physics, it might not have been R, it might have been F for like a force. Does that make sense? Okay. But jockeying around, interchanging variables, we can recognize that those formulas that you were providing in physics are just, again, 7th, 8th grade, 9th grade geometry. Okay, so, and in this case, Pythagorean theorem. So then we have tangent theta. Well, tangent theta is going to be opposite over adjacent, y over x. So then, in polar form, we are interested in that thing. Okay, we're interested in theta, so we take the tangent inverse. And you don't see this a whole lot, but if you think about it, that means that every time that you get an x comma y, you can change it into an r comma theta by taking the first coordinate of your ordered pair for r. And remember, this is r. It's going to be comma theta. You can take the first coordinate, and it's the square root of x squared plus y squared, and your second coordinate is always going to be tangent inverse of y over x. Okay. These two things are very, very important for us in regard to flip-flopping back and forth between
coordinates, okay, from one system to the next.
Is that something we can do? Let's take a couple other points and see if we can do this. Let's take the points. We'll just go 6 comma 6. Okay, so that point is 6 comma 6. If I take 6 comma 6, right now that's in rectangular form, and I want to change it into polar form. So R is going to be the square root of x squared plus y squared, right? X squared would be what? 36. Y squared would be what? 36. Would you guys agree that that looks like this? Square root of 36 times 2? I think it makes more sense to write it that way than to change it to 72. Because what's the square root of 36? 6. So it makes sense that your radius is 6 radical 2? Okay. Now theta, remember theta is tangent inverse. It's always opposite over adjacent, right? And your opposite is always the y value. Y is always going to be your opposite of theta. So it's always y over x. So now we go tangent inverse of 6 over 6, which is the same thing as tangent inverse of 1. Okay? What theta will give you a tangent inverse of 1? Pi over 4. So now this point, 6 comma 6 in rectangular format, is 6 radical 2 comma pi over 4 in polar format. And the way we can check that is using GeoGebra. I can type in 6 square root of 2. Now I got to use a semicolon so it knows that I'm talking about polar coordinates here, comma pi divided by 4. Hit enter. Does it give me the same point? Yeah, B is right on top of A there. Okay, and you can even do this. You can right-click on 6, 6 and click polar coordinates, and it will change it into polar coordinates. Now it doesn't change it to exact, pi over 4. Okay, rounds it to whatever decimal place here, and it doesn't change it to 6 radical 2. But that is an option. I don't know if it's got. Let's see here, surd text A. Text B. Yeah, it doesn't give me what I'm looking for there. Can we do that? Is that hard? No, that should have been pretty easy for us to do. Now, a lot of times, just like in the rectangular system, there's a lot of points that are not convenient in the rectangular system, right? There's a lot of rational values, irrational values, things that are kind of hard to plot. Might be the same situation in polar. We saw that with, that first example. We did 53.13 or degrees, or 9.3 rate or 0.93 radians is not a real convenient location to plot, right? We might have to ballpark or guess to some extent where those points exist. Is that right? Okay, or estimate. Do we need to do any more examples of converting from rectangular to polar? Okay, let's do polar to rectangular. Let's go the opposite direction. Okay, so going the opposite direction, okay, let's say that I have the point just for the sake of the work being a little bit easier, let's say I got the point 4 comma 4. Okay, and that is in rectangular format. Okay, if I move over 4 units this way and then 4 units up, I get that point A. Let's change that to
Let's change that to I guess I want to go from I'm sorry, I messed up. I want to go from polar to rectangular, right? Polar to rectangular. So let's just do this. Let's go 8, comma, and just do pi over 3. All right, so let's take that point. Okay. And like I said, it was 8, comma, pi over 3. Okay, so that's my r, and that's my theta. I want to change that into an x comma y. Okay, so you're seeing that it looks a little bit bigger than 4 on the x-axis, and it looks a little bit bigger than probably 7 on the y-axis, right? So those are going to be the numbers that we're interested in seeing here. And I'm going to actually leave these as exact values. I think we can do that here because of the theta that we chose. When you do this, you guys need to realize that that 8 that we just determined is the length of that thing right there, right? Okay, that is your hypotenuse, isn't it? Okay, so let's put 8 right there. We're going to draw a picture of this. And there should be, that triangle there existing, correct? I don't know this. That's what I'm looking for. I'm going to call it X. I don't know that. That's also what I'm looking for. I'm going to call that Y. Okay. Do we know that theta? What is that theta? It's pi over 3, isn't it? Okay. So, Katoa, how do I find X? Cosine. Cosine of theta, which is pi over 3, should equal X over 8, shouldn't it? Adjacent divided by hypotenuse. Can I multiply both sides by 8? And now what is cosine of pi over 3? It's a half. Does X equal 4? Does that make sense? Okay. Now when I go and want to find Y, isn't Y opposite pi over 3? So which trig ratio would you use to find Y? Sine. So I go sine pi over 3 is equal to Y over 8. So 8 sine of pi over 3. What's the sine of pi over 3? Radical 3 over 2. So does that give me, what, 4 radical 3 as my Y value? And then if we plot that point, 4 comma 4 square root of 3 in rectangular format, it puts that point D right on top of point A, doesn't it? So if those two things are the same, one in polar, one in rectangular. Now how does that kind of help us with a formula? Okay. Let's look at this thing right here. Let's look at that right there. What was 8 out of your polar point? It was R. So you're going to replace that 8 right there with R. What was pi over 3 from your ordered pair? Theta. Okay. There's your formula that will be consistent every single time, because at every single point that I have in polar form, if I connect it with the pole with a segment, it is a hypotenuse of some right triangle, right? So that adjacent, opposite hypotenuse relationship will always exist. So x will always be equal to r cosine theta. Okay. Now, can I do the same thing down here? 8 was r. Pi over 3 was theta. So there's my formula to go from r comma theta to finding a y. Okay. So very similar formulas, right? R cosine theta, r sine theta. Okay. The way I remember it is because people mess them up. Okay, because they'll interchange the x and the y and say that r cosine theta is equal to y. Cosine and x. Cosine compared to sine is alphabetical, right? Cosine comes first. X compared to y is alphabetical. X comes first, right? So I always pair up cosine and x because respectively, in their groups, they should come first alphabetically. Does that make sense? Okay. Sine and y, they respectively come second alphabetically. Okay, so that's how I always know which ones go with which ones. Now, in physics, maybe you used like r cosine theta equals A and r sine theta equals B, okay, or something like that. You've seen, hopefully at some point, similar formulas, and they were just provided for you, and you were forced to remember them. Maybe when you're doing questions with inclined planes and stuff like that, this is where it comes from. Okay, not too bad, right? At any point, if you ever forget those formulas, draw the right triangle, relate it with SOHCAHTOA, and you should be good to go. So that leads us into the next kind of concept here. I'm going to skip a couple slides as you're going through these, and we'll see enough of these in the next couple days that you're going to get enough examples, okay? But if you need more examples, there's some worked out examples here of how to go from, in this case, 4 comma pi over 4 to 2 radical 2 comma 2 radical 2. A couple other practice problems you can go through as well. But I want to talk about this slide here. Now, I know it might not be the most convenient slide to look at, but just kind of stuck with the size of things. Okay, so within rectangular systems, within rectangular coordinates, we have families of graphs, right? We have lines, we have parabolas, we have quadratics, or parabolas, cubics, quartics, we have all kinds of things, right? Logarithms, exponentials. Those are all families of graphs. Well, inside polar coordinates, we also have families of graphs. Okay. Now these families of graphs, obviously, they're things that you've never seen before, so it's going to be kind of a learning curve at first. We could spend weeks and weeks on this stuff. I'm just going to kind of glaze over because I think if at any point you need this stuff in the further math classes that you go into, it's going to be explained because this is actually not used a whole lot. And I can't remember in my undergrad work. Now, obviously, my undergrad work can be completely different. I took a lot of math classes. You know, Zach came in last week or the other day, and he talked to us. He's taking a lot different math courses, right? More engineer-based math courses. So maybe in an engineering course or a robotics course, maybe you would use these. I don't know. But I never use this stuff until I start taking graduate courses. Okay, so in the event that I think you guys end up needing this, I think your math skills will be strong enough to learn it. Okay, or to go. But I want to open your eyes to it and explain some of the stuff to you. There is a question on the final about this, and we'll definitely address that type of question, but I'm not going to get too deep into this information. But we have abilities of graphing polar graphs. It's just not as convenient right now as maybe the techniques that we've learned to graph rectangular equations. Okay, but the one strategy that you have used before, and it's kind of the first strategy we always use with a new set of graphs, family of graphs, is we develop a t-chart, right? And we just start plugging in independent variables, okay? And then seeing what the dependent variable turns out to be, okay? Now, when we were dealing with functions and stuff like that, the independent variable was the x's, right? Okay? Theta is actually the independent variable here, okay? And r is going to be the dependent. And that's because we know what the sign of certain thetas are. Okay, we know the sign of theta as well, so that's what I'm choosing here. So let's say that I've just got the list here of thetas between 0 and 2 pi. Okay, so let's just plug in 0. Okay, so if theta is 0, I get back. What's that going to turn into if theta is 0? I got their t's right now, but changing the thetas. If theta was 0, sine of theta would be 0, right? So I get 2 plus 2 times 0, which is just 2, right? Okay. So you can do all these ordered pairs and then go back and plot. I'll just go ahead and start plotting them as we go. So we go to this ray here, this 0 radian ray, and we'll go out to the second circle. So the second circle would be, about right there. Okay. One kind of intricacy about graphing polar graphs is it matters where you start, and it matters where your next point goes, so that once I plot this point and I plot a second one, I'm probably going to connect them right away. Okay. So I'm just going to choose another theta. Let's say theta is pi over 6. If theta is pi over 6, okay, what does this thing here turn into? 1/2, right? So I have 2 plus 2 times 1/2. What's that give me? 3. So pi over 6 ray is right here. I'm going to go out to the third circle. So I get that point there. And like I said, connect those with a smooth curve. It's not a straight line, it's a smooth curve. Okay. I'm then going to try the next one, which is pi over 3. Okay. So I get 2 plus 2. Sine of pi over 3 is radical 3 over 2, right? Radical 3 over 2. So that gives me 2 plus radical 3. Which I'm just going to ballpark that. That's about 3.7, I think. 2 plus 3. Yeah, 3.73. Okay. So I'm going to go out to pi over 3 ray, which is going to be this one here. And I'm going to go out to 1, 2, 3, and I got to kind of estimate. So about right there. Is that all right? Okay, so is that the right ray? Let's see. Nope. It's this one. And I would take a smooth curve there. Now I'm going to try pi over 2. Okay, so plugging in pi over 2 here, that's going to turn into 1. So 2 plus 2 times 1 gives me 4. So pi over 2, go up to 4. And I keep doing this, okay? Turns out there's some patterns here, okay? Once I get to 2 pi over 3, what's the y value for 2 pi over 3? It's radical 3 over 2, right? Haven't I already used a y value of radical 3 over 2? So shouldn't that, or not a y, a theta value of 2 pi or radical 3 over 2? Haven't I already used that? And that was with the pi over 3, correct? So does it make sense that this should be 3.7 as well? Does that kind of make sense to everybody? Okay. If I go to the next one of 5 pi over 6. 5 pi over 6. So 5 pi over 6, is that the same y value as pi over 6? Yeah. That 1/2 is the same as that 1/2, right? So when I evaluate, it should be the same as this line right here. So I should get an R of 3. And then I'm going to try pi. Well, pi is 0. I've already used 0 once. Gives me 2. So you see how we get those patterns? These values are repeating themselves? This happens a lot with these types of functions. Or maybe not functions, but curves. So 3.7 comma 2 pi over 3 is going to be about right there. 5 pi over 6, 3 is going to be right there. And pi 2 is going to be right there. I'm going to start connecting these things. Okay. Now, the pattern is going to change a little bit because now when I go to the other side of the unit circle, when I get to 7 pi over 6, my sine value is now negative 1/2, right? So now I go 2 plus 2 times negative 1/2. So now I'm going to be subtracting, so that gives me 1, doesn't it? 2 minus 1 there. So it's going to be 7 pi over 6 at 1. Find that. It's about right there. I'm going to try, I'm just going to skip a couple. I'll do this one here. This one's going to be easy. 3 pi over 2. Okay. That is negative 1. So I go 2 plus 2 times negative 1. What's that give me? 0. Okay. So at 3 pi over 2, it's this ray right here. I go to the 0th circle, which is just the pole, isn't it? So these points are coming in there. Okay. And then if I keep working around, maybe I try this one here, 11 pi over 6. Okay. That's going to be negative 1/2. Well, I've already used negative 1/2. It was the same thing as 7 pi over 6, so that'll be a 1. So at 11 pi over 6, I'm back out to the first circle. And these things are cyclic, so when I get to 2 pi was the same thing at, or put that on the wrong side. 2 pi is the same thing as 0, isn't it? So it gets me to 2 again, which will be that point. Okay? So you can see that curve that's created. Okay? Now, some graphing tools have this ability. R equals 2 plus 2 sine of theta here. Plug in theta. That's the shape we just came up with, right? Okay. What's that look like? I'm going to say a butt. Okay, looks like a butt. Something more. What if I look at it upside down? What it would look like? A heart, right? What is a heart doctor called? Cardiology. Okay. Cardio refers to your heart, right? Okay. This shape, okay, and it's anything that is of the form. Anything of the form sum A plus the same A sine of theta. Okay? So I can change that thing. Maybe I make that go to A. And that A, and it should ask me to create a slider. Well, let's do this. A. Maybe I can't create sliders. B. Okay. So let's say I say B plus B sine of theta. Everything of that doesn't know what that means. I'm going to multiply. I think I got to create a parametric equation. Maybe we'll do this tomorrow. But no, as long as the twos up there in that formula are the same number, so if it's 3 plus 3 sign, if it's 10 plus 10 sign, if there's 11 plus 11 sign, it's going to be some heart-looking shape, and we call it a cardioid. Okay? Because it looks like a heart. Okay? A lot of the names that we're going to come up with are weird. There's one called limicine. Okay? Limicine, I think, is French for the word snail. Maybe it's not French, but it refers back to snails. There's roses. Okay? There's just kind of, because that's what their images kind of look like. Okay? There are spirals. Your TIA 384 has this ability. Okay? All you have to do is go to your mode. And if you go down to the fourth line, see where it says function, parametric, polar, and then sequence? If you go highlight polar, it's going to change your y equals to r equals. Then you can type in 2 plus 2 sine theta and graph it. And when we graph it, it does look the same. Okay? Now the scale's all messed up because that's what the TIA 384 does when you zoom in. I like GeoGebra. I haven't dealt too much with GeoGebra. I haven't dealt too much with Desmos and dealing with polar graphs, but it's a better option. There is an 8.1 assignment available. Due on Monday. Thank you. You too. See you. You too. Thank you.